This is a series of 6 videos on global optimizations. This topic refers to non-convex programming. In convex programming, a local optimal solution is also a global optimal solution. But non-convex programming, there may be many local optimal solutions that are not global optimal solutions. So our standard techniques, optimization techniques that uses local searches are not sufficient to solve this type of problems. Now, one fundamental problem in non-convex programming is the minimization of a concave function over a polyhedral set. And this is the formulation of such a problem. So we are minimizing an objective function f of x, where x is our decision variable. It's a multidimensional vector. And x satisfies a set of linear equations. And the function f has the property of concavity. Okay. So this is the problem that we're addressing in these videos. Now, this type of programs generally have many local optimal solutions that are not global optimal solutions. So the techniques that we will describe has to do an exhaustive search in this feasible region to make sure that we have the global optimal solutions. A well-known mathematician, Tuy, published a pioneering paper in the famous journal Soviet Mathematics in 1964. And this paper is, this is the reference of this paper. It's called Concave Programming and the Linear Constraint in the Soviet Mathematics, 1964, volume 5. So since then, a vast amount of research has been done in this area, including my own research during my stay at the University of California, Los Angeles. Now, a class of algorithms called conical algorithms, or often referred to as Tuy-type algorithms. So this type of algorithm will attempt to solve this type of problems, and including my own version of this conical algorithms. Now, for references about this, the material that we will be discussing in these videos, I'll give you 2 references. One is my own paper, co-authored by Professor Jacobson from UCLA, called Exhaustive Non-Degenerate Conical Processes for Concave Minimizations over Convex Polytope. It was published in Mathematics of Operation Research, 1986, volume 13. And the second reference is an excellent book, a really comprehensive book, authored by Rainer Horst and Tuy, called Global Optimization. And this book not only addresses this problem, but also many other related problems to this. So these videos are organized as follows. First, I will describe concavity, quasi-concavity, and pseudo-concavity, all 3 notions important to this topic. And second is I will describe the general form of the so-called conical algorithms. And then the next 2 videos is about an important topic. It's called simplicial partitioning. What simplicial partitioning does is it takes an n-simplex and subdivides it into smaller simplices. And I will discuss 2 important properties. One is exhaustiveness, introduced by Tuy and Tuy, and the next property is non-degeneracy that I introduce in my version of this algorithm that will ensure finite convergence. And finally, I will describe my own version of conical algorithm and then go through a detailed proof of convergence, infinite convergence, and also finite convergence. So let me define what a concave function is. So we have a multidimensional function from a subset of Rn, S, into R. So S is a subset of Rn, n-dimensional, and we assume it's convex. I remind you what convex set is. A and B belonging to S implies the line segment AB is in S. Okay. So definition, f such a function is said to be concave if for every A and B belonging to S and lambda a number between 0 and 1, f of lambda a plus 1 minus lambda b is greater or equal to the same linear combination but with the function value. So lambda f of a plus 1 minus lambda f of b. So this is the formal definition of a concave function. Okay, now, so this number here, because lambda is between 0 and 1, this expression here represents a point in the line segment A and B. So the function value of any point in the line segment A and B is in the same linear, is greater or equal to the same linear combination of the function value. So if we want to, like in n equal to 1, so n equal to 1, this is a concave function. So if I take A here and B here, and then I draw the chord, so this height is f of A, this height is f of B. If I take any point in here, so that's lambda A plus 1 minus lambda B, right? And I take the height here. So this point is f of lambda A plus 1 minus lambda B, and this point here, that point here will be in the same proportion like the in the line segment here. So that will be lambda f of A plus 1 minus lambda f of B. So concavity just says that the chord is under the graph. So that's what concavity is. And also function f dot is convex, then it's just this expression, but it's less or equal to. Or f is convex if minus f is concave. Okay? So that's the definition of a concave function. Now I'm going to list 3 properties that we're going to be using in our in the discussion of the algorithm. First one is that f concave is going to imply that f of lambda A plus 1 minus lambda B is greater or equal to the minimum of f of A, f of B. Okay, so the function value of any point in the line segment AB is no smaller than the value at the minimum value at the extremity of the intervals. Okay, and that's directly from this expression. We just replace f of A and f of B by this minimum, and then you get lambda plus 1 minus lambda equal to 1, and you will have greater or equal to the minimum. So this is a direct correlation of this expression. Now, so the minimum of a concave function on a line segment occurs at one of the extremities, either at A or B. So that's what this expression means. So this is a convex linear combination of 2 points. Okay, this will imply also the convex linear combination of any number of points. The function value at that will be greater or equal to the minimum of the function value at each one of those points. So when we do our problem that we are interested in, concave minimization problem, minimize a function f of x subject to ax equal to bx greater or equal to 0. Because of this expression here, remember that this is a polyhedral set. Ax equal to bx greater or equal to 0 is a polyhedral set. And if it's bounded, it's a polytope. And a polytope is the convex hull of a finite number of points called vertices. So therefore, the solution to this, the optimizer here, is among the vertices of this region, right? The vertices of the feasible region. And remember, in my previous video on linear programming, the vertices are associated with the simplex tableau of this set of equations. Okay, so the answer to our problem, minimization of a concave function over polyhedral set, reside in one of the simplex tableau, and we know there are only a finite number of them. So this is a very important property of concave functions. Okay, the next important property that we're going to need when we deal with the convergence of the algorithm is continuity. F concave implies f is continuous the function f is continuous on the interior of S. Okay, our function is defined from S to N. Then if f is concave, then f is continuous function except on the border of S. Okay, it's continuous everywhere except on the border, on the boundaries of S. Okay, that's an important fact, but I'm not going to prove it here. But it's an important fact. And the third fact that's going to be using also deals with differentiable. If a function, if f dot is differentiable, is concave plus differentiable, then we have this, the gradient of f at a times b minus a less or equal to 0. This statement here implies f of b is less or equal to f of a. Okay, so in this expression, delta f of a is the gradient. So it's a row vector composed of the partial derivatives of f. Okay, yeah, the function, the gradient at a times the vector b minus a, if that number is less or equal to 0, that implies that f of b is less or equal to f of a. This expression here, this statement here, comes directly from this. All we have to do is rearrange these terms and make lambda goes to 0, and you will get this this statement right here. Okay, so these are three properties among other properties of concave function, but these three properties are important to us when we deal with the convergence of the algorithm. Okay, so now let me define what quasi-concave is and also pseudo-concave. So definition. We're going to say that a function is quasi-concave. It satisfies this number one property, this property. Instead of this strong property, if a function satisfies only this one, we say the function is quasi-concave. So f dot is quasi-concave if f of lambda a plus 1 minus lambda b is greater or equal to the minimum of f of a, f of b. Okay, it doesn't necessarily have this property, but it does have this property. So then if we are instead of a concave function, we're minimizing quasi-concave function or polyhedral set, the results still hold that the optimizer is among the vertices and the simplex tableau of the set of equations. So this is the definition of quasi-concave. And quasi-convex is quasi-convex if minus f is quasi-concave. Okay, so for quasi-concave, the function value is less or equal than the maximum at the extremities of the interval. Okay, so that's a quasi-concave. Obviously, concave implies quasi-concave. Okay, we just seen it here. But the reverse is not necessarily true. Okay, so for example, you take this function like this. Okay, a function like this. This is a monotone function. Any monotone in n equal to 1, we are at n equal to 1 dimension, okay? Any monotone function is quasi-concave and also quasi-convex. So this is quasi-concave, but not concave, right? It's not concave, it's actually convex, okay? So the reverse of this is not necessarily true. Okay, so that's the quasi-concavity. And the other point that I want to make is that quasi-concave does not imply continuity. Okay, remember that concave is continuous almost everywhere. Quasi-concave is not. So we lose, by just assuming this property, we lose the continuity. For example, if I take step function, okay, step function like this, in n equal to 1, this is quasi-concave, but it's not continuous. As you can see at this point, it's not continuous. Okay. So you're going to see that most of the results in the proof of convergence are going to be valid if we just assume quasi-concave and continuity. Then we don't need to assume the strong assumption of concave. Okay. Now the other definition we want to introduce is pseudo-concavity. Pseudo-concavity has to deal with this number 3 property that I just put. So definition: f dot differentiable if a function f is differentiable is pseudo-concave if delta f of a times b minus a less or equal to 0 implies f of b is less or equal to f of a. So if a function satisfies this number 3 property, this property, then we say that the function is pseudo-concave. Right? So obviously concave plus differentiable implies pseudo-concave. Okay, we just saw it over here, but the reverse may not be true. In other words, a pseudo-concave function may not be concave. Okay, and let me give you just a couple of examples just to tie up all these properties. So we take n equal to 1 and f of x equal to x cubed. So this function is like this. Right. So clearly this function is, this function here f is quasi-concave. Right, because it's monotone function, it's an increasing function. So it is quasi-concave, but it's not pseudo-concave. all right? Because at 0, you see f prime is equal to 3x squared, and f prime at 0 is equal to 0. So if you plug here a equal to 0, this equation is satisfied, and that means that the function value at any point b, I'm sorry, this is a. Then the function value at any point b is less or equal to a function value at 0, which is 0. That's not true. Right? So this function is not pseudo-concave at 0. This relationship is not satisfied at x equal to 0. So pseudo-concave implies quasi-concave. Okay, and I'm not going to prove that here. Okay, but the reverse is not true by this example here. A differentiable quasi-concave function may not be pseudo-concave. Okay, and the last example I want to show is the same thing: n equal to 1 and f is equal to f of x. Little variation on this. I'm just going to say x plus x cubed. So f prime of x is equal to 1 plus 3x squared. Okay, so this function looks almost the same as this, except the tangent at 0 is not 0, so it looks like this. So this function is pseudo-concave. Okay, you can prove it very easily, but not concave. Okay, obviously it's not concave. It has a portion that's convex. So the general relationship is concave implies pseudo-concave implies quasi-concave okay, for differentiable functions. But the reverse is not true. The reverse in here is not true, and the reverse here may not be true. Okay, so that's the three definitions: concave, quasi-concave, and pseudo-concave. Okay, so later when we deal with the convergence of the algorithm, we can replace concave with a continuous quasi-concave, but we're going to also, pseudo-concave is we're going to need that when we prove that my algorithm is finitely convergent. We're going to need this property here that concave function have. So if we replace the concave assumption by quasi-concave, and if we replace the concave assumption by pseudo-concave, then pseudo-concave we have quasi-concave, and all the theorem of the algorithm remain valid. Okay. So now, why are we interested in the minimization of a concave function of a polyhedral set? So this is the problem we are concerned in this video. So minimize a concave function over a polyhedral set. So this is the problem we are interested in. And remember, the linear programming problem is minimize C transpose. It's a linear form subject to AX equal to B, X greater or equal to C. All right, so that's the linear programming. And in my previous video on linear programming, we showed why this problem is very important. It has many real applications. Okay, so the C transpose X is a linear form. So C transpose is both concave and convex. It enjoys both properties of the concave function and property of the convex functions. Okay, so now we extend this problem to have the function being concave. And why we do that? One, there are many reasons for that. Okay, one is economies of scales. Okay, so in here, okay, so let's say we are modeling a factory or something of that nature. Here, this level of production. Okay, and this is the cost. So this one here, C transpose X. So this is linear programming. Right? We assume that the level of production, if we decide to manufacture X units, okay, then the cost is just C times X. There is a unit cost, and you multiply the level of production by the constant C. So the unit cost is the same. It doesn't depend on the size of the factory, of the size of the whatever model you have. So C is fixed. But in many models, there are economies of scales. In other words, that if we decide, so X is a decision variable. It could be at this level of production, small level of production, or very high level of production. When you go to higher level of production, the unit cost generally will decrease. In other words, we're going to be following a curve that looks like this. All right. Why does it decrease? Well, for one thing, if you are at a high level of production, you're going to make large order for raw materials, and generally there are discounts for large order for raw materials. So that will then impact the unit cost. You see, the unit cost on this curve here is the tangent to this line, and you see that the tangent of this line decreases as we decide to make our production much higher. Okay, so that's one thing. Two, if we decide to make a larger factory, then we're going to have efficiencies in the production process. We may automate many part of the production process, and that will result in lower labor costs. So the unit cost would decrease, all right, and other things. So this is in models that has economies of scale. This graph here is more reasonable than the linear cost. Okay, so that's one thing. Two. From a theoretical point of view, let's look at integer programming. Let's say that we have a linear program. We have linear program, same as the other one, minimize C transpose X, subject to A dot X equal to B. But here, my decision variable, some of them are integers. Okay, let's say you're modeling an airline company, and one of the decision is how many airplanes you want to buy. So that number has to be an integer. So the problem is the same as this, but some variables are integers. Let's see, the first R variable are integers, so let me assume they are 0 or 1. All right, they are modeled as binary variable, 0 or 1. And then the other variable are continuous variable. Okay, so this is an integer program. So this is no longer a linear program, it's an integer program. So generally this problem are hard to solve. But this problem here, this problem is equivalent to minimize C transpose times X plus P. P represents a very large number, a penalty factor, and then here the sum of I equal 1 till R of xi times 1 minus xi, and subject to the following equation, ax is equal to b, the same as here. X1, xr are variable between 0 and 1, and xr plus 1, xn greater or equal to 0. So I say that these two problems are equivalent, okay? And P is some penalty factor. It's some large number, okay? Now, so as you can see from here to here, we got rid of the integer part. So this here doesn't have any integer part constraints, okay? We just made the variable between 0 and 1, continuous variable between 0 and 1. But we added something in the objective function, that we are minimizing this with the C transpose X plus this term, okay? Now, why these two problems are equivalent? Because any feasible solution to this problem, any x that satisfies this, satisfies also this. Okay? And because xi is equal to 0 or 1, then this term is 0. So any solution to this problem is a solution to this problem with the same objective value, C transpose x and C transpose x. Okay? But here, for other solution that are not integers, 0 or 1, then this term is non-zero. And because P is large enough, it makes the optimizer of this problem to be the same optimizer as this problem. Okay, so but now this function now, this function is concave because right, this is xi times 1 minus xi, 1 and 0. All right? So each one of these functions is concave. All right? The sum is concave, so the whole thing is concave. So an integer program, which is generally a very hard problem to solve, is equivalent to minimizing a concave function over a polyhedral set. Okay. And there are other mathematical problems that could be formulated as minimizing a concave function over a polyhedral set. A third class of program that be converted to minimization of a concave function over a polyhedral set is what's called DC program. Which is the minimize g of x minus h of x subject to ax equal to b, x greater or equal to 0. So my objective function is the difference of two concave functions. So g dot and h dot are concave. Okay. So this is what's called a DC program. Okay. Now, this problem can be converted to my concave minimization problem by just putting, for example, this h into the constraint. So it's just like minimize g of x minus t. So I introduce a new variable called t, subject to h of x greater or equal to t, ax equal to b, x greater or equal to 0. So simple by adding a new variable. So now this is concave. Okay. And now this set here, this is convex. Because h is concave, so h of x greater or equal to t is called like a level set, and for concave function, level set are convex. So this problem here is can be converted to minimizing concave function over a convex set. So now, why is this problem important? Because most all functions are DC functions. So this is called a DC function. From Stone-Walser's theorem, every continuous function could be approximated by polynomials over a compact set. So every continuous function could be observed by polynomials, and polynomials, you can prove that they are DC functions. So basically, this problem right here, a DC program, is kind of a vast, rich set of programs that involve a lot of functions, okay, like polynomials or whatever function. As long as it's continuous, then it can be approximated by a polynomial, which is itself a DC function. And therefore, the concave minimization problem, our main problem, is a very important problem in optimization. It's kind of a bridge between convex optimization, which we know how to solve very well, and non-convex optimization. So now let me describe the general form of the what we call conical algorithm, or often they are referred to as Tuy-type algorithm. Okay, after the mathematician Hogan Tuy, who pioneered this area of research. Okay, so we have our CMP, minimize of a concave function f of x, and here I'm going to assume a specific form of the polyhedral set. I'm going to assume it's defined by linear inequalities, okay, where b is strictly positive. The vector b, each entry is strictly positive. Later on, when I describe in detail the algorithm, we're going to see how to transform any polyhedral set into this form using phase 1 of the simplex algorithm. Okay, so what this says here is that x equal to 0 is a vertex adjacent to exactly and other vertices on the axis. Okay, so in 2 dimensions, n equal to 2, this polyhedral set ax is equal to x greater or equal looks like this. These are the vertices. So x equal to 0 is adjacent to exactly 2 other vertices, is neighboring vertices. Okay, so we assume that my feasible region is like this. Okay, so iteration 0 then I'm going to define alpha 0 to be f of 0, alpha bar 0, x 0 equal to 0. Okay, so this is, I'm going to plug in x equal to 0. I know it's a solution to this because b is strictly positive. So I plug in x equal to 0, and I call it alpha bar of 0, x 0. So alpha bar of 0, x bar of 0 is the best solution I know at iteration 0. Okay, that's the only solution I know in the beginning of the algorithm. Okay, and also we can say that ax, the set less or equal to b, x greater or equal to 0, this set here is inside the cone C of 1, 0, 0, etc. 0, 1. Like here, this cone here, this is 1, 0, this is 0, 1. So the cone C of 1, 0 and 0, 1. Okay, this cone here, the non-negative orphan. So I know that my feasible region, this is my feasible region. It's inside this cone. So what's the idea of Tuy? Remember that for this problem, the concave minimization problem, a local optimum may not be a global optimum. Because of that, standard technique of optimization using the gradient and so forth are not going to work for this case. So we have to search every area of the feasible region. We have to search everywhere, okay? Because even though we have a local optimum, it may look like a global optimum, but it's not, all right? So we have to search every area of the feasible region. And the way we do it is we're going to subdivide this cone into much smaller cones, right? For example, here, this is C1, C2, C3, and C4, okay? And we're going to search every cone for a better solution, okay? So initially, when we start the iteration, we only have one cone to search. Okay, initially we only have one cone. Now, let me describe the general iteration of the algorithm. Okay, I call it Q. All right. So I am at iteration Q. I have alpha bar Q and x bar Q. This is the best solution I know. Okay. As I am going through the algorithm, I'm going to have some feasible point. I'm going to calculate the objective value, and then I'm going to update this value. So alpha bar Q and x bar Q here, alpha bar Q is equal to f of x bar Q. Okay. So this is the best solution that I know at iteration Q. And I also have I have a number of cone to search. Okay. So, for example, at iteration 0, I started with only one cone. As I go, I'm going to introduce new cones, and I'm going to subdivide other cones into smaller cones and so forth. So at the general iteration Q, I have a number of cones that I need to search for a better solution. So that's what we start with. So now, step 1, we're going to pick a cone. Okay, from this set of cones. Okay, I'm going to pick a cone. So this assumes that I have a selection criteria. Okay, when we describe the algorithm in detail, I'm going to propose 2 methods for selecting a cone among other cones. So we're going to select the cone that most likely will help us find a better solution. Okay, so that's the number 1. So and I'm going to call this cone C of Z1 Zn. Okay, a cone is defined by the extreme ray. So if we are in n dimension, all our cone will be n dimensional. So Z1 to Zn are in n independent vector. So it's a cone. So for example, C2, so this will be defined by Z1 and Z2. If I select this cone Z2, it's defined by 2 vectors, Z1 and Z2. So this cone here, every cone that I have here is identified by its extreme rays, okay, by n independent vector. So I pick this cone. Okay, so now I have, again, in 2 dimensions. So I have a cone like this, Z1, Z2, and then I have my feasible region. Okay. So now the question is, are there points in here that are better than the points I have, that the best solution that I have? Okay. So the first thing we do is, step 2, is calculate these points here, the points on the boundary. So I'll call this delta of Z1, delta of Z2. So here, compute the boundary points, delta of Z1, delta of Zn. Okay, that's very easily done because all I have to do is plug, let's say, Z1 here and then see what multiple of Z1 makes this inequality. Okay, so that's very easily done. And then since these are feasible points, then update automatically. I do, since these are now potential solution, then I update alpha bar Q is the minimum, all right, of the current alpha bar Q, and f of delta of Z1, etc., f of delta of Zn. Okay, update my objective function, the best solution, and x bar Q. Also, it's just argmin. Well, alpha bar Q is just the function of x bar Q, etc., f of delta of Z1, etc., f of delta of Zn. Okay, so I update my best solution since I have now new points. So I do update this. And then step 3, what I'm going to do is I'm going to search along this line, the extreme rays of the cone. So let me erase these. So step 3, and I'm going to refer, it's called the alpha bar Q extension of delta of Z1, etc., delta of Zn. Okay, this is terminology, is Tuy terminology. So what it means is that I'm going to search. So now, remember, alpha bar Q is the best solution that I know so far. So therefore, it's less than the function value at this point, less than function value at this point, and at this point. Right? So what I'm going to do, I'm going to continue on this line till I hit, I'll call it here Y1, and here call it Y2. Okay, so compute yi equal to lambda I times delta of Zi, okay, where lambda I is the maximum of lambda such that f of lambda Zi is greater or equal to alpha Q. Okay, so I'm going to go search. This is just a line search, which is easy to do. We can use binary method to do it. So we're going to search on this line, and I go as far as I can, but not being less than alpha bar Q, my best solution. So for this case, I get this point, and for this extreme ray, I get this point for n equal to 2. This is n equal to 2. Okay. And here, in general dimension, so this is I equal 1 till n. So now, and this is the Tuy idea that generated all this research for this conical algorithm. Now, if I draw the line or the hyperplane, so now we consider the hyperplane formed by y1, etc., yn. Okay. Remember, the zi are independent, so the yi are independent. So you have n independent vector, so they define a hyperplane. So, and the equation of the hyperplane, and then if I form the matrix, if I want to find the equation of this hyperplane, then I form the matrix D equal to y1, etc., yn, this matrix here, then the equation is just E transpose times D minus 1 x equal 1. That's the equation of that hyperplane, where E transpose is just a vector of ones. All right. So that's the equation of the hyperplane. So in 2D, to find the equation of this line, it's just this equation right here. So now, what is the idea now? So what can we say? If we look to this n simplex, so formed by 0, y1, etc., yn, right? This like here in this case, in this triangle. Any point in this triangle is a convex linear combination of 0, y1, and yn. And because of concavity, because it's a convex linear combination of that, then the function value is greater or equal to the minimum value at these points here. But each one of these points, their function value is greater or equal to alpha k. Then in this simplex here, f of x is greater or equal to alpha bar q. Right? Any point in this simplex, the function value is greater or equal to it by concavity. So therefore, the question is, are there points on the other side of the plane? I know that any point under this plane, the function value cannot be better than the one I have now. So the question is, are there points on the other side of the plane? And the way to tell that is by solving, then we solve the LP, which is maximize E transpose D minus 1 x subject to AX less or equal to B and X belonging to the cone CZ1, etc., Zn. Okay. This is a linear program. Okay. So we are in the smaller cone, AX less or equal to B, but X is belonging to that. So this is an LP, a linear program. Okay. So here we are at step 3. All right. So we calculated. So we have a cone. We calculate the boundary points, and then we went as far as we can, being greater or equal to alpha bar q, and we calculated the y1, y2. So we have our solution alpha bar q, x bar q. All right, and then the y's, yi equal to lambda I delta of zi. Right, where lambda I is the maximum lambda, so that the function value at yi is greater or equal to that. And then we form the matrix D equal to y1, etc., yn, right? And then the hyperplane, and then the linear program, gamma equal to maximum of E transpose D minus 1 x, such that AX is less or equal to B and X belonging to the cone. So this is where we are. Okay. And I said there are two cases. Okay. So the first case, case 1, is when I calculate y1, yn, and I did the hyperplane here, and I did this maximum. I went in and solved this LP. I found that gamma, so case 1, gamma is less or equal to 1. Okay. Remember, at this level, it's equal to 1. So less or equal to 1 is this way. So this feasible region is under the plane. So therefore, any point in here is a convex linear combination of 0, y1 through yn. So the function value cannot be less than alpha bar q. So there is no need to search. So no need to search this region here, defined by C, by cone C, right? There's no need to search here. We cannot find a better solution. So what we do is we just delete the cone from the search, and then we proceed to the next cone. We'll go to another iteration. So that's that case. Okay. Case 2, we are in this situation. So we did the same thing. This is the y1, but when I maximize, case 2 is gamma is bigger than 1. So this is equal to 1, this is less or equal to 1, and over here is bigger than 1. So I found out that, well, I do have feasible points that are on the other side of the plane. So in this case, we don't know. We don't know whether there are a better solution or not. We don't know whether the point above the plane, we know that the point under the plane are no better than the point we have, but above the plane we don't know. So what we do here is we split the cone into smaller cones. So we take this cone and split it into, let's say, 2 or 3 subcones. Make the cone smaller because it's easier to search a smaller cone than a larger cone. All right? And then, so we take this smaller cone and put it in our list of cones to be searched. Okay? And we proceed that way. All right? So this, so we have, therefore, we have a method of subdividing a cone into smaller cone. Right? So this assumes, the conical assumes that we have at hand, if you give me any cones, I can then divide it into smaller cones and make sure that the union of those smaller cones is equal to the original cone, so we don't lose any portion of the feasible region. So 2 things in the conical algorithm that we need to be aware of. Number 1 is we need to have selection criteria for which cone to pick. And 2, we need to have a method when we are in this case, we need to have a method of subdividing a cone into smaller cones.